Hello, everyone. I hope everyone is doing all right with their final exams and final projects today. My name is Jerry Frost, and today I'll be presenting about nowhere dense sets. Just an overview of my presentation today. First, I'm going to go over the textbook definition as to what nowhere dense sets are, found in 3.5.3. Then I'm going to go over an exercise proof found from exercise 3.5.8 to kind of show you the way to prove why nowhere dense sets are nowhere dense. It's kind of a two-way proof. And then finally, I'm going to follow up with some textbook examples, um, exercises 3.5.9 to show you what somewhere dense sets look like, what dense sets look like, and what nowhere dense sets look like. So first, the definition from 3.5.3. A set E is nowhere dense if the closure V contains no non-empty open intervals. Um, and just to go back there, the definition kind of means that the closure of E basically just has an empty interior. For the exercise that we want to prove for this definition, 3.5.8 asks us to show that a set E is nowhere dense in R if and only if the complement of the closure of E is dense in R. So the first half of this proof, first we're going to assume that a set is nowhere dense in R. A set E is nowhere dense in R. And according to that definition, the closure of E does not contain any non-empty open intervals. And then from there, we could choose any two numbers, x and y, in this set of reals such that x is less than y. And since the closure of E does not contain any non-empty open intervals, the interval of x and y cannot be a subset of the closure of E. And this implies that it's a subset of the complement of the closure of E. And from this, there must be some arbitrary element T that's within the complement of the closure of E, such that T is between X and Y. And then from there, the complement of the closure of E is an open set since the closure of E is closed. So therefore, the complement of the closure of E is dense in R. So now for the second half of the proof, when we flip that, we let the complement equal the closure of E be dense in R. And then from there, when T is an element of the complement of the closure of E, such that T is between X and Y, this means that the complement of the closure of E contains all open intervals, and the closure of E does not contain any non-empty open intervals. So therefore, by definition, E is nowhere dense. So if the proof was a little complicated, hopefully I can take you through some textbook examples to kind of clarify things more to show you what nowhere dense sets look like. So here we have exercise 3.5.9. It asks us to determine if a set is nowhere dense, dense, or somewhere in between. So you guys can pause the video, write this down, and go over any notes before I give you the answers. So the examples A and C are what somewhat dense and dense sets look like in R. For the first one, it's the intersection of Q with the interval 0, 5. And since part A has a non-empty open interval, it can't be nowhere dense. And it also cannot be dense either because there's no element Z between X and Y that fit the requirements written below. And also an example of a set that's dense in R is the set of irrationals because its closure is rationals, and then every point of R is a limit point of A. So hopefully that's an idea of what dense sets are. So now we'll look at what nowhere dense sets are. So the first example of a nowhere dense set is found in part B, where B is the set of 1 over n for natural numbers, and the closure of that is its union with the zero interval. And since the closure of B does not contain any non-open intervals, it's nowhere dense. And for part D, the Cantor set does not contain any intervals, so therefore it could easily be said that it does not contain any non-empty open intervals. So that was just kind of a quick presentation. I couldn't really go into too much detail for the time restraints, but hopefully you guys learned a thing or two from my presentation. And thank you so much for watching.